In this lesson, we're going to work through a word problem that involves a rational equation. Our word problem is going to involve a boat that's traveling with a current or against a current. Before we take a look at our word problem, let's just think about a boat traveling in a current. Here we have a boat traveling at a rate of 10 miles per hour in still water. Let's let the first boat be in still water. That means that this boat is going this direction at a rate of 10 miles per hour, or in 1 hour the boat is going to have traveled 10 miles. Now for this second picture, the boat is still traveling at a rate of 10 miles per hour in this direction. But we're going to make a change here, and we're going to let the current be moving in the same direction at a rate of 5 miles per hour. Now as you can imagine, the boat is going to get to its destination a little bit faster because you have the 10 miles per hour that the boat is traveling, and now you have the water carrying the boat a little faster at a rate of 5 miles per hour. So the effective rate that the boat is moving is at a rate of 15 miles per hour. Now let's take a look at another scenario. For this third picture, let's say the boat is now moving in the opposite direction. It's heading back to its original destination. It's still moving at a rate of 10 miles per hour, and the current is still moving in this direction at a rate of 5 miles per hour. This means that the current and the boat are moving in opposite directions. And again, as you can imagine, this is going to slow the boat down. It's going to slow it down by a rate of 5 miles per hour. So we could take 5 miles per hour away from the 10 miles per hour and see that the boat is really just moving now at a rate of 5 miles per hour. There's something else I'd like to look at before we begin our problem, and that's how the units work in a situation like this. If we're trying to figure out how long it takes for the boat to get to its destination, we're going to be dividing the number of miles that the boat travels by the rate that the boat is traveling, or the miles per hour. Or we could write it like this: miles over 1 divided by miles per hour. And when dividing fractions, you multiply by the reciprocal, so that would give us miles over 1 times hour over miles. And then from here, we could cancel out miles divided by miles, which just gives us a 1 and a 1, and the unit we end up with is just hours. Now looking back at our boat up here, let's say we're trying to figure out how long it takes the boat in each of these three scenarios to get 60 miles. We could say 60 miles divided by the rate, and for the first one that would be 10 miles per hour, which would give us 60 divided by 10 equals 6, and our units would be hours. Now for the boat traveling at 10 miles per hour with a current that's traveling in the same direction at 5 miles per hour, we would have 60 miles divided by the 10 miles per hour plus the 5 miles per hour of the current, or 60 divided by 15, which would give us 4, and the units are the same, 4 hours. Now for this last scenario, we would have the 60 miles that the boat is traveling divided by the 10 miles per hour that the boat is traveling minus the 5 miles per hour that the current is traveling against the boat, which would give us 60 divided by 5, or 12 hours. So for the boat to travel 60 miles in still water, it's going to take 6 hours. For the boat to travel with the current, it's going to take 4 hours. And when the boat is traveling 60 miles against the current, it's going to take a full 12 hours. I think now we're ready to take a look at our problem. A boat travels 18 miles per hour in still water. The boat travels 10 miles downstream and then 10 miles back upstream on a river with a constant current. The trip takes 1 hour and 24 minutes, and the question is, what is the speed of the river's current? Let's begin by setting up this equation. The unknown value is the speed of the river's current. That's what we're looking for. So let's let x equal the speed of the river's current. On the first half of the trip, the boat is going to travel 10 miles, and it's going to travel at a rate of 18 miles per hour plus the rate of the current, so 18 plus x. And we're adding because it says that the boat is traveling downstream, and the current is going to be moving in that direction. Then we'll add the second half of the trip, which will give us plus 10 divided by the rate of the boat minus the rate of the current, because now the boat is traveling against the current. And we're going to set all of this equal to the time it takes for the boat to make the entire trip. We don't want to write out 1 hour and 24 minutes in our equation, so let's take a second over here and figure out how to write 1 hour and 24 minutes as a fraction. We'll write it as a fraction of an hour. There are 60 minutes in an hour, and over here we have 60 minutes for this 1 hour plus the 24 minutes here, so that's going to give us 84 minutes. And now let's go ahead and reduce that, because both of these numbers are divisible by 12. We can reduce this to 7/5. So let's put 7/5 in our equation down here, and that'll give us 10 over 18 plus x plus 10 over 18 minus x equals 7/5. All that's left at this point is to solve for x. There are a couple of different ways to approach this problem, but what we're going to do is we're going to multiply each term by the least common denominator. And the least common denominator is just going to be 18 plus x times 18 minus x times 5. So let's set that up. When we multiply the least common denominator here by the first term, you can see that the 18 plus x divides by 18 plus x, and that gives us a 1, or it cancels. So for our first term after it's reduced, that'll give us 5 times 18 minus x times 10, or just 50 times 18 minus x. For the second term, when we multiply by the least common denominator, the 18 minus x and the 18 minus x will reduce to 1. And that's going to give us 5 times 18 plus x times 10, or just plus 50 times 18 plus x. And then for the last term, or the expression on the right-hand side of the equation, we're going to have the 5 and the 5 to reduce, and that'll give us 18 plus x times 18 minus x times 7, or 7 times this conjugate pair, which I'm going to go ahead and multiply together. And that's going to give us 18 times 18, which is 324, and then minus x squared. Now let's simplify that, and let's find some space up here to work. So we're going to use this white space here. So as we multiply or distribute this 50 with this 18 minus x, that's going to give us a 900 minus 50x. And then for this next term, as we distribute the 15 to the 18 plus x, that's going to give us plus 900 plus 50x. Then on the right-hand side of the equation, that's going to give us equals 7 times 324, which is 2,268, and then multiplying the 7 times the minus x squared gives us minus 7x squared. We can simplify this left-hand side by combining the minus 50x and the plus 50x to give us 900 plus 900, which is 1,800, equals 2,268 minus 7x squared. We could then add the 7x squared to both sides, so that would give us 7x squared, and then take away the 1,800 from both sides, which is going to give us 468. Then we could divide both sides by 7, and that's going to give us x squared equals 468 divided by 7, leaving that as a fraction for now. Once we take the square root of both sides to undo this square, normally with a quadratic we would say plus or minus square root, but at this point a negative speed for our current doesn't really make sense. So we're going to disregard the negative, and when we take the square root of 468 over 7, we get approximately 8.2. That means that the speed of our current is about 8 2/10 miles per hour. Now you know a bit more about solving word problems that involve rational equations. See you next time.